Hey, everybody. Welcome to our sixth lesson for social justice math. We kind of hinted at what we're going to be doing today at the end of lesson 5, but we're going to take a look at something we call hypothesis tests in this one. So this is going to be a way that we can evaluate the proportions that we've collected, right, through our sample data and things like that, and also evaluate what we're being told about proportions from other people, whether those be just other human beings we come across, whether those be studies, whether those be private or government entities, anything like that. So quick recap of proportions to make sure we've got the things we need for this. So let's suppose we want a proportion of people who are happy, right? Then what we would do is we would take a sample and we would find our sample proportion. That's our p hat. So this little guy with the hat right here. Find our p hat, just the number of people in our sample who are happy, and then over the total number of people in our sample. So everybody we asked, that number goes on the bottom. Everybody we asked who said that they're happy, that goes on top, right? So we take n people and survey them. We find that x people are happy, right? Then we would get p hat as x over n, right? And we're going to eventually compare this to our population proportion, where we look at the kind of ideal number in this scenario. So we're total size of our population and then the actual number of people who are happy for the entire population. So most of the time we can't find this. That's why we do a sample, right? We use p hat to estimate what p is, right? P hat being our sample proportion, p being our population proportion, right? But one of the problems we ran into last lesson was we did not really have a way to evaluate how good of an estimate it is. The only real thing we were able to come up with is make our sample bigger, and that makes it better, but even that isn't quite enough sometimes. So just another point of notation that we want to talk about here, right? If we want the proportion of people who are not happy, we just do 1 minus the proportion of people who are happy, right? Because either you're happy or you're not happy, right? Those are two things you can be, right? If you're not happy, you could be melancholy, you could be sad, you could be angry, you could be lots of other things, but we're kind of all grouping those together. So when we look at our non-happy people, we'll call that Q hat here at the bottom, but that's a Q hat, right, for our sample, or a Q for the population. It's going to stay Q for our non-happy people, our proportion here, but it's just a matter of whether it gets a hat or not. It gets a hat if it's talking about the sample, and it doesn't if it's talking about the population. So what we want to do is we want to investigate a way that we can take these proportions, but then also figure out how good they are, right? So in order to do that, we need to form a hypothesis, right, which is a claim about our population proportion, right? So we're going to do this, and then we're going to use what we call a hypothesis test to test whether or not we think that claim is valid or not. So here are some examples from last time of claims, right? 60% of Mobilians prefer Carpe Diem coffee to Starbucks, right? That is a claim about a population proportion. 24% or 24.7% of full-time Springfield College students are first-time first-year students. That is another claim about a population. So in this first one, our Mobilians are our population, so everybody lives in Mobile, right? And in this one, all of our full-time Springfield College students, those are our population, right? And we're making some sort of claim about what people in that population think or say or would do in a certain scenario. So translating this into math, since these are populations, right, we would have that P is 0.6 in the first one for the 60% of Mobilians, right? And then the second one, we'd have P is 0.247 for our full-time Springfield College students that are first-time first year. So we're just taking these percents, we're just converting them to a decimal. That's all we're doing. So now let's break it into the pieces we need for our actual hypothesis test. So we're going to need two things here. We're going to need a null hypothesis. We're going to need an alternate hypothesis. So null hypothesis is the statement that our population proportion equals some value. So to go back to our example from last slide, the way we would write this mathematically is H naught. It's our null hypothesis, H with a 0. Sometimes when the 0 is in the subscript, people will say null or not, right? So H naught instead of H sub 0, colon, and then P equals 0.6, whatever our statement is. right? The other one we did, H naught colon P equals 0.247, right? So what we're going to do is we're going to assume at the start of the test that that is true. That is going to be kind of the information we're given. That's going to be something from a previous study, something we're being told, right? Or kind of our current understanding of what's going on. And then at the end of the test, we're either going to reject that claim, saying we think it's wrong, or we're going to fail to reject it and say we don't have enough evidence to think that it's wrong. So the other thing we need is our alternate hypothesis, and that's H sub 1. And this is a statement that our proportion is in some way different than what we're being told. Right. So this is kind of our what we actually think is going on. Right. So if we have H naught colon equals 0.6 for the number of Mobilians who prefer Carpe Diem, we could think that number is higher. Right. We could think more people like Carpe Diem over Starbucks. We could think it's lower, in which case more people would prefer Starbucks to Carpe Diem than we thought. Or we could just think it's not equal, meaning it could be higher, or it could be lower. We just don't think it's exactly 60, right? So here's some examples, right? We would have H naught colon, same as before, just with an H1, right? So H1 colon, P does not equal 0.6. This would indicate that we think it's just different than 60%. We don't think it's exactly 60% of Mobilians that prefer Carpe to Starbucks. We just think it's different, maybe higher, maybe lower. We could have H1 colon P is less than 0.247, right? So if you remember, that was the number of first year college students at Spring Hill out of our full-time students. So that was our proportion for that. So this would be us saying, we actually think that there are fewer first year freshmen at Spring Hill College. Or we could go the other way and we'd say, actually, we think there are more than that now. We think our first year recruiting class was bigger, and it's actually a higher percentage than 0.247. So that would be H1 colon P is greater than 0.247. So we got three symbols to play with here: not equals, where we just think it's different; less than, where we think that the proportion is smaller than we're being told; and greater than, where we think the proportion is bigger than we're being told. Right? And all this information is going to come from either the problem statement that you're given or the situation that you're in. Right? You're going to have some bit of information you're being told. That's going to be your H naught. And then you're going to have some hypothesis about what is actually going on, that something has changed, that something is different, or that something up here isn't right or correct. And so that is going to be our alternate hypothesis. So easy thing to remember this, right? H naught has to have an equal sign in it. H1 has to not have an equal sign in it. H1 can have three different things: less than, greater than, or not equals. Right, but it can't have an equal sign, and H naught always has to have an equal sign. So let's look at these statements and see if we can mathify these words, right? Turn them into a null and an alternate hypothesis. So this one, the proportion of SHC students that enjoy ultimate frisbee is greater than 0.55, right? So if we did that, our H naught would be that it is 0.55. It is what we're being told. Our H1 would be that we actually think that percentage is bigger. So we would say H1 colon P is greater than 0.55. Right? 98% of SHC rugby players have a vertical leap over 30 inches. Right? So this one isn't giving us a keyword like here. This one told us greater, and that's what told us to use this greater than sign. This one isn't giving us anything like that. Right? So it's asserting that exactly, specifically, 98% of rugby players have this vertical leap. And so the way we would test this is we would just think it might be different, right? It doesn't tell us necessarily that it might be bigger or smaller. We don't have an inkling there, but we just think it might be different. So we're being told it's 98%. So we have H naught colon P equals 0.98. And our H1 is going to be H1 colon P is not equal. So it could be higher, could be lower. We just don't think it's the same, 0.98. All right, so our last one here, the proportion of TV viewers that enjoy CBS is under 15% or 0.15. So under being the keyword here, right, telling us we think the percentage is smaller. So our H naught would be that P equals 0.15. And our alternate hypothesis, our H1 would be that P is less than 0.15. So the basic idea of what we want to do here, right, is we have our P that we're being told. Well, you have what we're being told is our proportion for the population. And then we're going to collect a sample and we're going to find our p hat here, right? And our p hat, right, is going to probably not be the same number as our p, right? And that could be because the sample we got just leaned one way or the other, right? The average was a little off, the proportion was a little off, right? The samples aren't going to have the same number as our population in almost every case, right? So what we say is, we know this is off, but how likely is it to be as far off as it is, right? If it's just a smidgen off, then it probably has a high probability of being that, right? It's not far away from what we expected. So that's probably just, some randomness in there, a little bit of statistical noise. And so we say, that probably occurred by chance. There's probably nothing actually going on crazy. And so we're going to fail to reject H naught, right? We don't have enough evidence based on the data we collected to say otherwise, right? Our data doesn't give us enough of a pause to say what we're being told is wrong. Now, on the other hand, if we take our sample and it's way off, right, then it has an extremely small probability of being way off, right? And so what we're assuming here is, okay, well, if we're being told the truth about our population proportion and I get a sample that's way, way off what I expect, then the likelihood that that occurred just by random chance is really low. And if that's really low, well, then the likelihood that something else is going on has to be really high, right? So if this is a 1% chance that we got a sample that we did, given that our population proportion we're being told is the truth, then that's a 99% chance that our population proportion we're being told is not it, right? So what we're going to say there is, if there's that significant difference, then we're going to reject H naught and we're going to accept H1. So rejecting H naught means we have enough evidence based on the data we have collected to say that we think H naught is incorrect and we think that H1 is the actual thing that's happening. So that leads us to the question, well, what's our bar, right? How strange does our sample proportion have to be in order for us to actually determine that something's not quite right here? So we have to know, did it occur by chance, right? And to do that, we're going to use something called a z-score, which is a test statistic, right? And this is just kind of a way to take population proportions and sample proportions from different contexts and scenarios and kind of standardize it into one nice, neat little package that mathematicians and statisticians and you can use in every possible situation. So we have a formula for calculating the z-score. It looks beefy. I promise it's not actually that bad, right? So our z-score here, right, we're going to call z star for our test statistic. So this star will indicate that came from our sample. This is our test. And what we're going to do is p hat minus p, so the thing we got from our sample, minus the thing we're being told about our population proportion. So sample proportion, population proportion. And then all of that's going to be over this big square root. And in the square root, we're going to have p, again, our population proportion, 1 minus p, all over n, so how big our sample was. So this is how we're going to find our test statistic z. Now, I do want to be clear, right? This formula may not be difficult from a mathematical perspective, but it does have some moving parts to it. And we want to make sure that all those things are where they need to be. So we have two things up here in the numerator, and then we have our fraction, a square root, and then a fraction in the denominator. So what you're going to want to do is make sure you get a little bit of practice putting this into your calculator, right? So that you get the right answer, because if you don't put this in correctly, right, then there's a chance that your calculator will misunderstand what you're trying to say and give you a wrong answer. So maybe something where you're doing the math completely correct and your setup is great and you're kind of cruising, and then you plug it into your calculator and your calculator misguides you. So fun note about calculators, they can do things really quickly, right? They can add, subtract, multiply, and divide, and they can look up things in their memory really quickly. And that's it. That's all they got. So calculators are fast, but also very stupid. So if you don't tell them exactly what you want, they will become a genie and they will warp and twist your equation into something that does not give you the right answer. So spend some time practicing that. So if we have, right, Starbucks claiming our actual proportion of Mobilians who prefer Carpe Diem to Starbucks is 0.6, but our sample set was 0.8, what we can do is find a test statistic by using these two numbers, right? So we would have 0.8, that's from our sample, so that's our p hat. 0.6 is what Starbucks is telling us, right? So that goes for p, right? And we're testing to see if that's accurate. So we have this as our p. So anytime I see p, I put 0.6 in there. Anytime I see p hat, I put 0.8. And n is the only other thing we have here, and that's going to be our 400 Mobilians, right? That's how big of a sample we have. That's how many people we asked. So in that case, right, we have to plug it into this formula and figure out what Z star is. So I'll leave that for you to do. Now, of course, we can get our Z star, but that's just a number, right? What exactly is that telling us? Well, we can use that to figure out how extreme our sample is, right? And by extreme, I don't mean like our sample is doing some rad skateboard moves. I mean, right, how extreme is it in the sense of like, how weird is it that we would get this sample, right? How far outside of what we expect is it, right? So if our Z star, the thing we got that we calculated is extreme, that's when we reject our H naught. That's when we say we think something's wrong here and we actually think H1 is what's going on because this is kind of wild, right? This is extreme. Whereas on the other hand, if it's not extreme, if this is kind of what we expected, then we would say, we didn't get enough evidence to really reject H naught here. So we're going to fail to reject H naught. We just didn't have the evidence to say it's different. Right. So how do we know if our Z star, right, our test statistic is extreme, right? What we're going to do is we're comparing it to a critical value. And for those of you who have actually taken stats before, you may recognize a lot of this stuff we've done so far, and you would know that there are ways to figure out exactly what that critical value is and exactly how we would compare it. And right, so we'd have like a p-value and a test conclusion. But for now, we're going to simplify it a little bit. So we're just going to assume a significant level of 1% or 0.01. And what this means is we're going to fail to reject our H naught unless, right, there's less than a 1% chance that we got the sample we did given that our p-value we're being told is correct. So I'm going to repeat that again because that's a lot of stuff here, right? So we are going to reject our H naught only if there's less than a 1% chance that what we're being told is correct and we got the sample we did that was as extreme as it is. So basically what this means is we want to be at least 99% sure that we are correct before we jump out on a limb and say, actually, we think Starbucks is lying to us, right? Once we put those words out there, that's not something you can bottle up, especially on the internet. Nothing ever gets deleted from the internet. So we want to make sure that we have a really good shot at being okay with this before we put something like that out there. So here's going to be our benchmarks, right? Depending on what is going on in H1, right, what symbol is in there, we're either going to have a greater than, we're going to have a less than, we're going to have a not equal sign, right? One of those three. Those are the only options we have. So if we get a Z-score for our test statistic that is beyond this boundary, we're going to reject H naught. So if we have a greater than, we're looking for bigger than 2.33. So greater than 2.33, less than negative 2.33. Right. So remember, less than with negative numbers, I'm talking -3, -4, -5, stuff like that. Right. So negative and then a larger number. Right. So -3, 3 is larger than 2.33, but because it's negative, it goes backwards. Right. And then if we have a not equals in here, it's going to change up the number slightly. We're looking for either bigger than 2.575 or less than negative 2.575. right? So if you think about a number line, right, we either want bigger than or smaller than what we're doing. So we're kind of looking for these outside edges of the number line, right? Anything in the middle is kind of represent what we expect to happen. And the farther we are away from the middle, right, the weirder our sample is. So if we got a sample of, or a test statistic for our sample of 0, that would be like dead on what we expect, like absolutely 100%, like makes total sense. But if we got something like 3, right, and we had a not equal sign, we would say, I don't know, I would like closer to 0 is better. 3 is bigger than I was kind of hoping for. And this is our cutoff. This is our, we're going to be right 99% of the time cutoff, right? So if we're bigger than this, the 2.575, or smaller than negative 2.575, we can say, I think something's fishy here. So I'm actually going to skip examples 1 and 2 right now. We're going to come back to them in a little bit. I think I'll post this on Canvas, kind of worked out, but I want you to take a minute to work this. I put these up in an order that I think is less beneficial for this video's sake, but better for class. So I'm going to skip over this real quick. We're going to go to example 3, and I'm going to do 3 and 4, and then we'll come back to 1 and 2. So let's suppose, right, that Mars, right, the candy company, claims that a fun-sized bag of M&Ms is 30% red M&Ms. Right, what we do is we take a sample of 25 M&Ms and we find 11 of them are red. Right, and so we're going to use our significance level of 0.01%, which for us right now just means that we're going to use the chart from previous to figure out whether or not our sample is extreme or not. So let's set up our hypotheses here, right? We've got H naught is that P equals 30%, or P is equal to 0.3. We use decimals, right? That's what we're being told the proportion is. And we are just going to test to see whether that's true or not. We don't have an idea of whether it might be higher or lower. We just want to see if it's different. So what I need is I need a couple numbers here, right? I need my p-value and my q, right? So 0.3 and 0.7, that comes from what we're being told. 0.3 is our p-value here. And so I do 1 minus that, and I get 0.7. That's going to be our q. Our sample size was 25, and then our p-hat was 11 over 25. 11 of the M&Ms in our 25 M&M sample were red. Right, so we get those 4 numbers, and we're pretty much good to go. So once we have this set up here, we just plug in all the numbers where you see them. Now, one difference from this to the formula we talked about before is right here in the denominator. When we talked about it before, we said P times 1 minus P, and now it's turned into P times Q. So this is totally fine. Remember, how do we find Q? We just do 1 minus P. P is 0.3. Then I do 1 minus 0.3. I get 0.7. So it's really the same thing, but you'll see this formula pop up with both variants there, either P times 1 minus P right here in the bottom, or P times Q. So I wanted to show you both just so you're aware that they are in fact the same thing. All right, so 0.3 goes here for P. Everywhere we see P, we get 0.3. 0.7 goes for Q, right? This 11 over 25, if we actually figure out what decimal this is, that's 0.44, and that goes in here for P hat. And then we have in our sample is 25. That's our sample size there. Work all this out, we get 1.53. Now, since we have a not equal sign in our H1, that tells us that our critical value is this plus or minus 2.575. So I either need to be bigger than 2.575 or smaller than negative 2.7 or 575. 1.53 is not bigger than 2.575. Right? It's definitely not smaller than negative 2.575 because it's not even negative. So this isn't extreme enough for us to say that something's wrong. So in this case, right, we would fail to reject H naught. Right? We don't have enough evidence based on the data we've collected to say that the proportion of red M&Ms in a fun-size bag is different than what we're being told. Okay, let's go to something a little more real life. So according to the U.S. Census Bureau, of the members of the U.S. population 25 or older, 32.5 have a bachelor's degree. Right? So this was a few years ago. in a Census Bureau sample of 31,020 Hispanic Americans, only 15.5% had at least a bachelor's degree. So we're going to test again at a 1% level of significance, so alpha equals 0.01. If this disparity is just random happenstance, right, standard statistical variation, or if there's something else happening, right, that might be lowering the number of bachelor degrees that Hispanic Americans get. Okay, so let's pull the info we need from here, right? We have 32.5% of Americans age 25 and older have a bachelor's degree. So if that works for all Americans, we would assume, right, everything else being equal, that would hold for every subset of Americans, right? As long as it's an adult 25 or over, we would assume that 32.5% of males have a bachelor's degree, 32.5% of females, 32.5% of African Americans, 32.5% of Hispanics, right? We would assume that carries over from all Americans to any subpopulation we wanted to look at, right? So that's going to be our null hypothesis here. We're going to say H naught is going to be that P equals 0.2 or 325, right? It's going to be that our Hispanic Americans should have the same proportion of bachelor's degrees as all Americans. Now, clearly, from our sample, this is lower, right? 15.5%. So we have to figure out whether that's a statistical anomaly, right? If we just got a weird sample when we did this here, or we have to figure out if there's something else going on. Either way, our hypothesis is going to be, we actually think that fewer Hispanic Americans have a bachelor's degree, right, on average than like all of America. So we would say, we think the proportion of Hispanic Americans with bachelor's degrees is lower than what we're being told. So hence the less than here. Now we're going to collect the same information. So I'm going to stop for a second and I'm going to let you see if you can figure out what numbers from here go into this, right? Because I'm going to tell you right now, this is the hardest part of the problem. If you can figure out how to read this word problem and get the right numbers over here, you're golden, right? So spend a minute, see if you can figure that out. All right, so hopefully you've had a chance to look at that. Let's take a look at our N. Our N is our sample size, right? And they tell us we had a sample of 31,020 Hispanic Americans. So that would go there, that would be our N. Our P hat is our sample proportion. It's only 15.5% of our sample had a bachelor's degree. That 15.5% is going to be our P hat, or if we want to convert it to a decimal, 0.155. P is always going to be the same as what we say it is in our H naught up here. So we've kind of already figured that out. So I can just drag that 0.325 down here for P, and then I do 1 minus that, and I get Q. So here are the numbers we come up with for that. Now, we have our formula, so we're going to go ahead and plug all our numbers in and stuff. Plug it in just like before, plug it into your calculator, and what you should get out is negative 63.926. Now remember, right, less than here, we were looking for our Z value to be less than 2.33. That was our benchmark. That was our goal line, right? Anything smaller than that tells us that we think there's something else at play, right? We're 99% sure at least that there's something else going on. So we're not just like talking about 3 or 4 or 5 here, right? We are way out, right? This is a very extreme Z value, right? This Z value is at the X Games. That's how extreme this thing is. So in this case, right, being way smaller than our benchmark, being way smaller than negative 2.33, we would reject H naught, right? So we would say, actually, we don't think Hispanic Americans are getting bachelor's degrees at the same rate as other Americans. We think there's something else going on. Now, to be clear, we cannot say from this information what we think that thing is that's going on. We just know that something else is going on. So this is a good place for us to kind of start an investigation into this and see if we can figure out what the cause is, but this will not tell us what a cause is. So let's go back a little bit. Let's go to our examples 1 and 2. Right, so let's say a friend claims that they can always pick a majority of college football winners in a given weekend. So if we give them 16 games, right, they can always pick a majority of winners. Now, if our friend was completely crazy on this, we would expect, right, with 16 games and two possible winners for each game, they would get about half of them right? If they just randomly guessed, they should probably get half of them right because they have a 50% chance in each game, right? Now, if we convert that to our population proportion, we would say P equals 1/2. Right? We'd expect them to get half of the games. Right now, of course, I know there are sports fans out there yelling at me right now, right? Punching their computer screens. Obviously, there are other factors at play. Every game's not 50-50, but we're going to simplify it a little bit and assume, at least for this, right, it is. It's just a 50-50 coin toss between whether team A wins or team B wins. Right? So converting this to a hypothesis, we would say, well, we would expect our friend to get half of them right, and our friend is claiming that they can get more of them right. So what's our conclusion if our friend gets 12 winners right? Well, really all we need to do is figure out what our P hat and what our N are. Right? We have our P here, and if we have P, we also have Q. So those are the only two things we're missing. So 12 winners right out of 16 games, okay, that tells us 12 over 16. So that's 3/4, 75%. Right? So our P hat in this case would be 0.75. Right? And our N would be 16 games, right? That was our sample size. We gave them 16 games. Our friend got 12 right out of the 16. So 16 games is our N, 12 over 16 or 0.75 is here. P hat. Right? We plug it into the formula, we work it all out. I'll have an example of this on our Canvas page. What is our conclusion if instead of 12, they get 13 right? Right, so now, right, our P and our Q are still the same, right? That's still the same. The only thing that's changed here is the number they've gotten right. So we still have N equals 16 games, but our P hat has changed now to 13 over 16. So we run the whole thing back, right? We do the formula again, right? Our P stays the same, our Q stays the same, our N stays the same, but we're going to run the whole thing again with 13 over 16 being our P hat, right? We'll get a decimal for that. We'll plug it into the formula. And then let's see what happens with our critical value. So like I said, I'll post an example of this on our Canvas page, but do yourself a favor and see if you can figure this out using the other two examples we just did, because I think more than likely you'll be able to give this a pretty good run for its money. So with that in mind, we of course have our worksheet to take care of for this. We will have that due at the end of the week if you are in the summer course. If you are in the regular course, that will be due at the time of test 2. So thank you all for watching. I really appreciate your time, and I will see you in the next one.